watch the video as well if you need to. All right, so here we go. So we are told that A is a matrix and then X and Y are 2x1 matrices as well. And we're just asked, does these matrices have a linear transformation? So the very first thing we have to show is the additive property. And to recall the additive property, it is the one that's up there. I wrote L of A plus B is equal to L of A plus L of B. Basically, if we were to substitute A plus B into the same function, is it the same result as if I just added the two functions back together? So in this sense, we'll start off with trying to figure out what L of A plus B is. And this is going to be A, in this case, not an L, of X and Y rather than A and B. So this part right here is the same thing here. It's just they give us other names other than L, A, and B. All right, so this right here, same as that. We're going to prove this one first. To prove this, A is this matrix. So we'll say 7, -2, 5, -3, times the X plus Y. All right, so if I was to add X plus Y, how do I add matrices? Just add them. Now, granted, there are no numbers here, but if they were, we would just add them up. So our first element would just be x1 plus y1. And then our second element would just be x2 plus y2. If I was given an actual value, that would give me an actual number. Before I go on any further, any questions? Okay, so once again, we're trying to prove this statement. My A is my L. It's just named something different than an L. My X and Y is the same thing as my A and my B, but we're denoted with these things. So this is the same thing as this. Now that I know what A, X, and Y is, I plug that in. A is this matrix. My X plus Y would be this matrix. We're good? Now, how do I multiply matrices? Row times column. So let's do that next. So I'm going to take this row times this entire column. Because remember, this would be one single element in each one had I known what the value is. So so x1 plus y1 is one element. x2 plus y2 is one element. Again, if you knew what the values of x and y was, let's say x1 was 1 and x or y1 was also 1. What's 1 plus 1? 2. So you would get one single number. We just don't know these values. So that's what the point of proving kind of is. All right, so to write this out, I'm going to take 7 and I would multiply by this guy right here. Now, when I take a 7 times a binomial, what's that going to turn into? What would I do there? There we go. So it becomes 7. 1. And then it would also become what? 7y1, right? So we would take that 7 and have to distribute because it's technically like a binomial. All right. And then I come over here and I have a -2 times x2 plus y2. So I'm going to go -2 times x2 would give me -2x. Very good. And then -2 times y2. Very good. And then again, if I knew what these values were, all of this would become one single number. But we don't, so it's just written like this. Good so far? So with that in mind, on how I did that, how would I multiply 5 and -3 to this? What would it look like? Very good. Not 5, it would be the -3. The 5 multiplied to the top, the -3 would be multiplied to the bottom. So it'd be -3x2, then -3y2. Very good. All right. So now I'm going to pause there. That is what ax plus y is. Now I got to go figure out what in the world would these guys be. Now, I don't have an LA, so that would be represented by AX. I gotta go find out what that is. I don't have an LB, so I have to go figure out what is a Y. So I gotta go find out what these are separately so that I can add them up to see would I get something that looks like this. Again, before I go any further, how are we doing? This is the basis of today's lecture. We're gonna be doing this a whole lot. Go ahead. Yeah, we're just in the additive property. We haven't even proven the multiplicative property yet. All right, so we got the left side of the additive property. Now we're trying to determine what the right side of the additive property is. So AX will just be this matrix of A, which is 7, -2, 5, -3, times X, which in this case is X1, X2. So if I had to multiply this out, row times columns, what would this turn into? Perfect. That's it. All right. And then I would do the same thing to this row with this column, and what would I get? Perfect. All right. So now let's do the same thing with A and Y. A again is 7, -2, 5, -3, and my Y was equal to Y1, Y2. What would that give me? Very good. It'd be the same thing. So it'd be 7, Y1 minus 2, Y2, then 5, Y1 minus 3, Y2. All right, so what we just did is we just determined what these two guys are. Now we have to add these to see if it gives us this. Now, how do we add matrices? Just like each element, right? So I'm just going to take 7x1 minus 2x2 and add it to 7y1 minus 2y2. Obviously, I can't combine like terms, so I just write them out. So 7x1 minus 2x2 plus the element in 1, 1 there. So that'd be 7y1 minus 2y2. Then do the same thing to the bottom. That'd be 5x1 minus 3x2 plus 5y1 minus 3y2. Now, my question to you is this the same as this? It is, right? Here's 7x1, here's 7y1, here's -2x2, here's -2y2. Then you look at the top, the bottom, 5x1, 5y1, -3x2, -3y2. So this is verified with the additive property. Yes, but I wonder if we're assuming. Maybe, maybe. Hmm. I think the multiplicative one will be a lot easier. There's not much there going on. All right, so the multiplicative property can also add it into your journal. As again, if you recall from over there, we are trying to show LKX equals KLX. So I really just got to show one of these, either the X or the Y. So again, the L is the A, K will just be a random K, and then the X, oh, I think I put up there, I put X that time, will be my X in the situation. The only thing that's different is going to L is going to be the A. So I'm going to prove what A K of X is. So A would just be 7, -2, 5, -3. And then my kx, so that's going to be times kx, I guess technically would just be multiply both of these by k. So that'd be kx1, kx2. Now, what can I do with scalars? What do these both have in common? A k. So I could technically factor a k out. So would this be the same thing as this? Because if I distribute that k, when I get right back to where I started? Okay. Now I'm trying to get it to this part. So I want to move this k to the front. Can I do that in multiplication? Oh, I don't want to move it in front of the equal sign. I just want to move it in front of the A matrix. Very good. Yes, because multiplication is commutative. The order right here is not going to matter where I put that k. I can times it here or I can times it here. All right, so I'm going to move that k over. I say that matrices. What do you mean? Oh, because you're proving this point. So kx would be, well, all of these with a k in it. So if this was a 2 and a 3, yeah, just add a k to it. And then I was like, well, that's the same thing as factoring out a k, because if I distribute it, it would be the same thing. Now I'm just moving the k. So it's not that I know it. It's just I had to look at it. Oh, that's kx. Here's what x is. Let me add a k to all those. Yeah. So it's I mean, it's different in it's going to look different, but the process is really, all right, what are you telling me? Let me plug that in. That's what it looks like. Now I'm just trying to use algebra to manipulate it to what I want it to be, which is why I'm going to move the k over. No, k is going to be a scalar. K, remember, this is a scalar multiple is what that k is. So just like we did on lesson one assignment, when you had like L of 15 and you turned into 3 times 5, but then you pulled the 3 out as a scalar. So a scalar is just a number that's being multiplied. It dilates the function, right? It's not an actual matrix that's being multiplied. So that's a good question. Yeah. We're not seeing K as a matrix. It is like a random scalar multiple. So this could be the value of 5. Then I would know that this would be a dilation of 5, or K could be a 1/2. So now it's technically it's compression, but still dilate half the size and stuff like that. But that's a good question. Yeah. K would be just a single number, not a matrix. All right, where's my pen? There it goes. And so then when I rewrite this as 7, -2, 5, -3, and then x1, x2. So now all I'm going to do now is go back. K is just K. This is my A, and this is my X. Is that what I just needed to prove for multiplicative property? Yes, I pulled the K out and it gave me the same result. So both parts are proven. So therefore, this is a linear transformation. So a matrix is a linear transformation. And we kind of already knew that when dealing with complex numbers. When we dealt with complex numbers and we had dilations and rotations, what did we always end up multiplying it by? Not just the scalar. It was a matrix in this form here, right? So another note to remember from last semester. It's a matrix. So we used this matrix to identify rotations and dilations by using the modulus and the argument. But we plugged it in, worked it down, we would get like random numbers here, but those numbers turn into a matrix. So a matrix makes sense that it would be a linear transformation because it's literally shifting something in a direction. All right. Yes, sir. Ooh, perfect. Thank you. You too. Have a good weekend. So that's the thing. We don't have an L. Our L is the A. This is just a generic like property equation. In our situation, they named our L as the A. Then it would be KZX. You got it. And then if this was Z's and W's, then I would be trying to prove a Z or a W. Right? Any other questions? That's good. These are good questions. So let's get into our first exercise then. Don't know if we're quite ready to do one on our own, but we'll get there. Or are we? You think we could just do one automatically? We ready for the test? Yeah. It's okay. I don't expect y'all to be proofs are probably the hardest things to do in math. I'm gonna be honest with you. These proofs are the easy ones. Because at least you have numbers. We have proofs out there that have like no numbers, and it's really just writing an entire like page on something. And you're just like, I will always go back to my very first proof I had to do. It was abstract algebra, and I had to prove that a times 0 = 0. Abstract is just so you have linear algebra that's like matrices and straightforward. It's basically the algorithms and math, right? Abstract is thinking like outside the box and understanding how does the math actually work, rather than just knowing how to do the math. You're understanding like how is it affecting space in itself. That's why it's called abstract. You ever heard of abstract art? Yeah. So that's like it's like figures, random figures. You're like, this makes me feel sad. That's abstract thinking. Like, what is the map affects? And then we have fields and rings and theories and things like that that actually make our or axioms and things like that that make what we know as math. Now, when I teach it to you, a times 0 = 0 is because what? What else? Anytime thing 0 is 0. That was my thought process too. But then I had to use fields, rings, and axioms to prove. And it took me like probably about 3/4 of a page that anything times 0 is 0. Because I couldn't just say that. I had to use facts that showed that. And then those facts tell us that anything times 0. It is, but it's not an axiom. There's rings and fields and other theories and stuff like that that you have to use to prove it. So I'm never going to make you do that. It's always going to be some type of algorithmic process to just show that one side equals the other. Those are the nice ones. And then keep that in mind when we get the trigonometric proofs as well. Those are fun too. That is my goal to end the year off with that. Yes. All right, here we go. All right, so on this first part here, it says Explorer Challenge 1, the geometry of 3D matrix transformations. What matrix in R2, so that's all real numbers in a matrix of 2, so that's a 2x2 matrix, that's all this means, serves the role of 1 in the real number system. So again, this right here just means a 2x2 matrix. So what 2x2 matrix serves the role of 1? And that's written how? That, good. 1 0 0 1. And it is the identity matrix. Very good. 4, more time. So for, and that's what I was about that. Identity matrix for multiplication. Because would this be the identity matrix if I was adding? Very good. Which is leads us into the next question. Has everyone got A down? I'm going to erase and move on. That's it, right? Bringing facts back into this. Man, I don't know. I could talk about math, I think, literally all day. So let's go into the B. What matrix R2 again? When you see this notation, that's a 2x2 matrix. So I'm going to try to throw you off. What would this mean? I read it correctly. A 3x3 matrix. And if I was to replace it with a 4, that's a 4x4, and so on and so on. Go ahead. That's a good question. I don't think we really have a notation for 2x1. Yeah, it's going to be the same number. I got you. Yes. So if it's a 2, it's always going to be 2, 2. If it's a 3, it's a 3, 3. I don't think we have a notation if the columns and rows are different. I think we would have to note it as R and then like a 2, 1 to show that it's a 2x1 matrix or something like that. That's a good question. I don't think I've ever seen one like this. I'm going to assume no. So again, so what 2x2 matrix would serve the role of 0? Good. 0, 0, 0, 0. When I was grading y'all's lesson 2, maybe lesson 1, I forget which one. A lot of y'all, when y'all would get the answer 0, y'all just wrote 0. That's incorrect. If you get 0 for every element, it's the matrix. And I wrote it down. You'll see my notes in there. But it'll be like the matrix 0, 0, 0, 0. That's what you have to write. 0 itself, you're telling me that the matrix itself just turned into a scalar, which can't happen. Right? So just keep that in mind. It's a simple notation. I don't want you to mess up. But this would be for what role? Would a 2 by 2? There it is the additive identity. I think added. Is that just that? Why does that not look right? Added. Sure. Okay. I don't either. Additive identity. It just feels like I'm missing like a T or a D. Maybe I don't. I don't know. All right. There's a question over here. What was it? Yes, it was. Sorry, it's a comma. My bad. So yeah, so that 0, 0 has the role of the additive identity. We good so far? All right. Going to use these facts later in the lecture. All right. What is the result of a scalar multiplication of R2? What would I use as a scalar multiplication for a 2 by 2? We talked about it in the opening exercise. Just K. Very good. So a K would be our scalar multiple. That's all we're going to write there. And again, this is just giving us, I guess, what you would call universal language, so that when we start throwing stuff at you, and I put a K out there, we all know this is going to represent a scalar multiple for a 2 by 2 matrix. Solid so far? Really, this is just notes more than work. All right. All right, so this is where that's going to come in. So given a complex number, a plus bi, what represents the transformation of the point across the real axis? So what caused us? Okay, so I'll give you a generic one. Go ahead. Oh, I don't want the matrix yet, but we'll get to there. I like that. I like that. Let's say I have, we'll call this A and we'll call this B. And I have a complex point there. What would I need to do to reflect across the real axis? IA minus BI, right? Which would then come over here. That would reflect. What is that called? Conjugate. Very good. So you would need the conjugate. Lost. Okay, so this basically says take a complex number A plus BI. I don't know what A and B is. They look both positive, so I just randomly put a point there. And if I want it to reflect across the real axis, remember the real axis is the x-axis. So the x-axis, I need to come over here. To do that, I need a negative, not negative A, negative B. The A would still be the same value. So that would give me an A minus BI. My question then from there is, what is A minus BI? It is a conjugate. I think I spell it wrong every time. Is it the G first, then the J, or is it J, then G? Oh, so I got it right this time? Usually I always do G, then J. All right. The question's on that. Recalling back memories, right? All right. So now I think we're ready for the second challenge. I think we have enough of the stuff from last semester coming back to the forefront of our brain. All right, so is vector addition commutative? Meaning, does the order matter for addition? That okay, I guess I just wrote it right there. That means, does x plus y equal y plus x for each 2 by 2 matrix? And what about points in a 3 by 3 matrix? So to prove this, because this is all we're going to do is prove it. To prove that x plus y equals y plus x, we'll just let x, just like kind of like in the open exercise, be x1, x2. Yes, technically I should say actually, let, capital L. X equal this and Y equal Y1, Y2. All right, so that's gonna be our basis. So here's our question. X plus Y is what we'll show first. So X is now X1, X2, and then Y is Y1, Y2. Before I go any further, how are we doing? I know it looks like I'm just throwing letters with little suffixes numbers there, or subscript numbers, but I'm not. I'm letting X be this a two. It's technically a 2x1 matrix, but it would map onto a two-dimensional real number. For things, it would be so much easier to understand if we actually. Yes, it's easier to see it, but once you prove it, it's proved, and then all you got to do is know that you can do the math. So I get your point, and I want to teach it that way, but you have to understand it this way so that we can use it from here on out. So I got you. So if it helps, on a side note for you, just change this into 1, 2, 1, 2, and then show that it works out. Go ahead. Correct. So if we, yeah, that's a good point. If we were to just use numbers to try to prove it, those numbers could work, but maybe there's numbers that don't. If we prove it with letters, then all numbers work. We don't have to like go find a counter argument or something like that. Was there a question? I saw your hand kind of go like this. Okay, go ahead. Okay, because yes, we have control of X and Y, because it doesn't tell us what X and Y is. I just gave it a form in a two-dimensional plane. If you want it to, you could let X be X14 and X17. It doesn't matter as long as you have two elements that you put there. Hopefully that helped out. All right, so how do I add these vectors? That's it. X1 plus Y1, and then this would be X2 plus Y2. All right. Here's what I'm going to leave you. Find out what Y plus X is. Does it matter? Does it matter what numbers it's got? Oh, what do you mean number? Like that little subscript? That's a good point. Is regular addition of numbers commutative? Right? We're doing commutative. Yeah. Like is 2 plus 3 the same thing as 3 plus 2? Yes. So therefore, with inside the vector, I know regular number addition is commutative, and I could switch the order, making it look the same. Go ahead. Oh, that's how. So if you're asked to put something in standard position, it needs to be alphabetical order. So yeah, so let's do that. So if I do that, that's going to be y1, y2 plus x1, x, not lambda, x2. If I add these across, what did we get? And then Braid makes a good point. In standard position, we go alphabetical order, but we also know in addition, it is all commutative. Yes? Good. I already knew there was a mistake. I just had to look at it. Okay. And so I'm going to switch that order because in a regular addition in real numbers is commutative. So I'm able to do this. And are these two things the same? Perfect. You just proved it. So we now can state vector addition is commutative. So now we can just throw random numbers in there and do the work without having to prove it. Go ahead. Okay, so this is a 2 by 2 matrix, but this is it still in a 2 by 2 plane because it still holds. I see what you're saying. How do I explain that? So this represents all 2 by 2s in a 2 by 2 plane. This is a 2 by 1 matrix, but will still fall on a 2 by 2 plane. Versus when I go to a 3 by 3, this is where we talked about yesterday with the XYZ. We talked, and that's why I said yesterday, this is very important. If I have a point in this plane, my next point, even though it looks different, is still going to be on that same plane. Oh, and I threw the paper away. I cut out a paper for 6th period. We really showed it with a visual aid there. But so even in a 3-dimensional plane, the vectors that I'm adding will still fall in a plane that I can cut out in space. It'll still land on that same plane. Just not a XY coordinate, just more of a whatever coordinate, whatever plane you want to call it. We'll call it QT formula or plane or whatever you want to call it. Technically, when you change the plane from an XY, you can have a new plane of something else. You get to name it. I mean, there's not a specific name for any of it. Does that make sense? So even though I in a 3-dimensional one, I can raise it off. All right, here we go. Let's call this floor an XY plane. This coffee cup represents my vector. So that endpoint right there is the Z. This rising up off this floor is the Z. So that's my vector right there. Okay. I have these other vectors right here, right? Here's another vector. I can make a plane that will touch both of these as a two. Let's call this a random plane. I don't know the name of it because there's not a name for it. But this plane would have both of those coordinates 3-dimensionally in a 2-dimensional plane. Does that make sense? Yeah, I'm just cutting it out in space. So here's a vector, and here's a vector in a 3rd-dimensional plane, and I can cut it and have all those points fall in a 2-dimensional plane. Yes, and I could do that if it was a 3-2, 3-1, 3-3 even, but they would all be able to cut out in a single plane. It's just that plane is now in space, not our floor anymore. Does that make more sense? Maybe. I don't know. Yeah. Thank y'all for y'all's kindness. I don't know. It's that abstract thinking, super hard. The other alternative, you could just believe me and we could just move on. Either way works for me on that one. But I do want to make the understanding. If you have the question, it's just you have to think about it. Like, that when I was a student, geometry was my worst subject because I couldn't physically take this object and turn it into a 2-dimensional figure in my head so that I could find the solid surface area or understand the volume. It wasn't until I took calculus that I eventually was like, okay, this is basically just a big rectangle with 2 circles on it. It was at that moment I was able to dissect it. But in y'all's shoes, I had a hard time taking 3-dimensional objects and thinking about them 2-dimensionally. So I can see y'all be confused and hard to understand, but you gotta break it down. You gotta take these 3-dimensional things and see it in a 2-dimensional plane. So it allows us to continue to do our math. Just take my word for it. It's fine. However you want to look at it. All right. Any questions then on that? So we proved that vector addition is commutative in a 2 by 2, and it'll follow in a 3 by 3 as well, because I can cut it in a single plane, which is back to 2-dimensional. All right. So with that, move on to the next part of our proofs. Yes. That's why I said yesterday is easy. Today, you're not going to like it because y'all never like proofs. So my next question Is vector associative? What does associative mean real quick? If commutative means order doesn't matter, associative means no. Associative is grouping doesn't matter. Parentheses, grouping, which in this case does x plus y. If I was to add that vector first, then add it to the r vector, is that the same thing if I was to add the y plus r vector first, then add it to the x? We'll prove it in a two-dimensional, and then you can believe me that all three-dimensional objects can still be cut in space on a two-dimensional plane. It's just no longer the xy. That's why we don't talk about four dimension, because four dimensional is a lot harder and doesn't have the same application to it. And it's also really hard to graph. It is. Associative. Commutative, order doesn't matter. Associative, grouping doesn't matter. You're welcome. All right, so let's prove that. So to prove that this right here, I'm going to again, you can let it be whatever you want, Ileana. If you wanted to let it be V or T or Q or P or 418 or however you want to do it, you can do it. I like to keep it simple. I'm going to let X be X1 and X2. And I guess I should do this more like this. What's the correct, like comma? Nope. Y. I'm going to let Y be Y1, Y2, then an and when you're listing. R will just be R1, R2. But again, Eliana, if you want to call it different thing, you could draw Godzilla right there if you wanted to, and then have a stick figure there as your elements. You're letting it be whatever you want it to be. Just in your end result, there better be a Godzilla and a human thing or whatever in the same spots. That makes sense? Like you can let these elements be whatever you want. Okay. It just makes sure that it works for all Godzilla forms. You know, because then you gotta take about the different things. If y'all have watched any of those movies. Okay. I haven't played Fortnite like in 3 or 4 months. Yeah. Once they took the shield off, it was no longer fun to me. Oh, there's a sword now. Okay. I might jump back on. But they went back to classic and it was like back to like Call of Duty type stuff where you're just shooting people and people okay, y'all are teenagers and really good. I cannot jump and shoot and field at the same time. I need to do one thing. That's why I like the shield because I can just throw it and it's going to sling somebody and I can just wait for it to come back. Whatever. We're getting off topic. All right, so let's prove this. So we're going to first do the left side. I'll let you do the right side and we'll see if we get to the same conclusion. All right, to prove this left side, I'm asked to add the X and Y first. Then add the R. Again, when I add vectors, how do I add them? Good, and their corresponding elements. So this now becomes x1 plus y1, x2 plus y2. Now, once I've added the vector of x and y, I'm now going to add the vector of the r. And when I do that, what do? Yeah, this is just the left side. You'll prove the right side on your own. Good. This would still be one element had I known what the numbers are. So I'd still add it accordingly. So this would be x1 plus y1 plus r1, x1 plus y1 plus r1. All right. Do it. Absolutely. You're correct. I was making sure you were paying attention. You did good there. That's good. What I want you to do now is prove that this will give me the same result. So go ahead and try that. If I got the left side, you prove the right side. Do they equal? Yes or no? I'll promise you when I come back, we'll throw numbers back in with this. We just got to state these things so that we don't have to assume. We now know. Ready? Still see some pencils moving. Just make sure you're awake. Your pencil wasn't moving, and then it started moving again. All right, ready? All right, so the first thing I have to do is do what? I need to add the y plus r first. Now, here is the thing that gets a lot of students. When proving something, you might automatically see it and go, obviously, it's going to be the same thing, but you have to show all the steps. That's what proving's all about. All right. Even though we can just assume, like, oh, well, duh, it's going to equal this. As the writer, to tell the reader, you have to show the whole process. All right. So that's why I wrote it like this. Oh, not plus, equal. And now I'm going to add that as one vector now. So that's going to be y1 plus r1, y2 plus r2. And then when I add these, I then get the result of x1 plus y1 plus r1, x2 plus y2 plus r2, and there's a 1 there. And then therefore, do they equal? Yes. Do I need to demonstrate you again how I okay, so then it works also for 3 dimensions. We good? All right, let's work on the next thing that we have to prove and no longer assume. Will the distributive property work for vector arithmetic? That basically means will k times x plus y equal kx plus ky? All right. So we already stated in our notes beforehand that k does represent our scalar multiple. So we don't have to redefine that in our notes. We know that that's a scalar multiple in R2, which is what we're trying to prove. So all that was stated at the beginning for this reason, so I don't got to re-explain what K is. And then so now we're just going to let X be X1, Y1, and Y equal Y1, Y2. That's supposed to be a 2. That's supposed to be an X. What am I doing? Hold on. That's X2. My bad. My brain instantly, when I start saying X1, I go to slope for some reason. X1 minus X2. I don't know. All right, we're good? All right, so again, I'm going to show the left side. You're going to show the right side. So I'm going to, well, actually, we could probably do this all at once. So here's my K times my X plus Y. In this case, this is now my K times my X1, X2, plus my Y1, Y2. What do I typically do according to PEMDAS? Parentheses. So I'm going to add my vectors inside before I distribute. So this is going to be my K. And this is just going to be x1 plus y1, x2 plus y2. And then what do I do with a scalar multiple? Distribute to every element. Very good. So I'm going to write this more as K times x1 plus y1, and then a K times x2 plus y2. Then distribute within that section, which will then just give me kx1 plus kx2. Oh, man, talking about organization. That's a y1. x2, and then k, y2. All right, so now I'm here. Could I state, since I'm adding, and we know that addition is commutative and also associative, could I then rewrite this as k x1, k x2 plus k y1 and k y2? Could I write it like this and this be the same thing? Because what I know what happens with adding vectors. It's going to go back to this, right? Now let's go one more step further. Let's factor out this k like we did in the opening exercise. So now this is k x1 x2 plus k y1 y2. You're more welcome to write your k's like this, but that looks like a 1 less than sign to me. So I write it like a cursive k. We good? All right. We know that we let x1, y1 be x, and we let y1, y2 be y. So I can rewrite this one more time as kx plus ky, which is what I was trying to prove. Maybe. Make sure you take good notes. Any questions? And then you're going to trust me. That works for a third dimensional plane. All right. The other thing that make me do is I literally had to bring Desmos back out and prove it, but we saw that yesterday and y'all didn't like it. I thought it was super cool. All right, let's look at D. 2 minutes to do D. All right, so is there an identity element for vector addition? That is, can you find a point in a two-dimensional plane such that x plus a equals x for every point in x? Give it to me. Okay, so how would you write that as a vector if it's the origin? Very good. What would it be for, we'll put this R2 here. What would it be for a three-dimensional? Very good. All right. Questions on that? Didn't ask us to verify. It just asked us to find. So I'm pretty much done there. We good? I think there was one more for the additive inverse, and I think that would be the end of this lecture. So let me do this in a minute. Now I could do a long lecture on how to find this, but we're just going to tell you. All right. So does each element in R2 have an additive inverse? What does additive inverse mean? It means that if I add something to it, I get the value of 0. So if I was to let A equal, let's stick with our x's. If I was to let x equal x1, x2, what would y have to be so that it would equal 0? Negative x1, negative x2. So the moral of this story is the additive inverse is the, or basically, I guess, of x1, x2 is negative x1, negative x2. Basically, we just change the sign of each element. And that concludes it. So then when we get into lesson 7 next week, after y'all practice these concepts, we don't have to assume, we will know, and then we can do a lot more math with numbers. You enjoy the rest of the day, guys. Enjoy the weekend. It's supposed to be pretty.